Hello, welcome back. Can you hear me? Okay, thank you. Since we have half the class back, so I think the other half are still will be joining us briefly in short while. So let's pick up some new topic here, and the topic is processes. So any computing environment, especially the technology we have right now, utilizes processes. And look at a process from a very simple perspective. When you write a program, it's a process in a way, okay? But we'll define that, but let's look at it from that. So when it's performing a particular task, we can look at it as a process. But that is a very rudimentary definition. So let's now look at the really definition when we are looking at a process. Okay, so processes, okay, they are not central, but distributed throughout. Okay, so remember we have discussed about something being centralized and something being distributed. So they are distributed. So that means clients and servers and all the others have processes. And so they form the building blocks. So all the functionality that we have been talking about in a distributed environment, processes are the building blocks. So all those things that we need done, the processes are what helps us. But a process itself, the detail of a process, okay, is not sufficient, okay, for a distributed system. What do I mean? A process, we'll see later on, will require memory space, will require some management, will require allocation of resources to support it. So what we are saying here, the detail itself is not sufficient, okay? So we need something more refined to be able to help us here in terms of us supporting a distributed environment. So this brings me to the other one, which we call threads. There's a difference I'm going to mention, okay? The processes are actually threads, but there's a refined definition of that. So instead of just using, okay, instead of us just using processes, okay, we prefer to use threads, okay? And so that concept brings in there's something we call multi-threading. So it is easier to build distributed application using threads. I can build a distributed application using a process, but it is not the best to be able to use to build those applications. I need something that's refined. In a short while, I'm going to explain what I mean by being refined, okay? So most of the processes, okay, in most of the implementation, okay, we have a multi-threading operating systems. You will require that we use a multi-threading operating system. Means that we will require that we have processes that basically are refined so that it can handle the requirements. So a process itself, okay, a process itself is very, very heavy, okay? And so if we want to organize all our application, if we want to organize all our work such that each one will have its own memory space and so forth, that will become very, very heavy for that application. And therefore, the best thing for us to do is to try and organize it in terms of threads. So I'll talk about the difference in a short while. So I've said processes are key, but their detail is not sufficient. So we break them down into threads. And the threads will be able to run on a similar address space. Okay, so that's one of the things that we have to remember. And I'm going to maybe refine this definition in a short while. Okay, and so, but the key important thing that differentiates the two is that a process will require its own independent memory space. A thread will not. So a thread can share. So it means if I have a memory space, a thread can share with another thread that memory space. A process cannot share. So that means that I can have several threads using one single memory space, and that means I can now be able to multiply things. And remember, a process can perform a function the same way a thread and a process can perform the same functions. The only difference here, if you notice from this, from what I have given down here, okay, the difference here is saying I can have a thread with using very minimal space, which means that is shared, as opposed to using a process which uses its space independently. So if you can share things, it means you can multiply your capability. We'll expound that concept as we go on. Now, so here, so now coming to the definition, okay, a process is a program in execution. Okay, so it will have to be assigned somewhere in the process. I will assign it to be executed. Okay, so it can be a unit of activity. So execution of instruction, a current state. Okay, it might have associated system resources, but basically it's a unit of activity. Okay, it will have, of course, a program counter. It will have its code. It will have a code segment. It will have data data segment. So if you look at all those ones for a process, so we are saying a process has an address space and one thread of control. Remember this part here. This is a very, very important part to remember. One thread of control. So it's saying a process can only do one thing. Okay, one thread of control. So if you are doing, maybe you wanted to compute an average, it will only compute an average, regardless of whichever space you have given it. So one thread of control. Okay, so it's important to, and if I'm looking at it from a thread perspective, I might have several of threads using the same address space. And that means I have several threads of control. So that means I can do multiple things at the same time on the same address space. So when you're looking at this one thing to remember, why threads are much better in comparison to processes. Let's expound that, okay? So if I have a process or one program counter, so A starts, okay? Then let me use an arrow, so I think that so that it's easier. So A starts, then B, then C, then D. And you notice from here, the time variations vary from one process to another, from one process to another. And we have a process switch. A process switch means I was doing one task and I go and start doing another task. That's called a process switch. And you can see from this diagram, they all have different periods of time when each one is implemented. Some are shorter, some are longer. Okay, and from there, you notice that when you are having a process, you will have to have from one to another. And so looking at this diagram, I can see this one is one, it finishes, another one, and another one. You see, time is this direction. So it means that if I'm using a process, I must finish one before I go to another. Okay? So let's assume I'm giving a process tasks. So it must finish task A before it goes to task B, before it goes to task C, before it goes to task D. Okay, so even if we are talking about multi-programming, but still remember, we are looking at it from one to another to another. So the concept here, 4 independent sequential processes. So the implementation of a process is sequential, task sequential. One task must be done, and then we go to the next task, and then we go to the next task, and we go to the next task. Yes, it is good, but is it efficient? Because remember, as we set up processes, we'll give each one of them its own address space. Okay, so only one program at an instant is active, given that address space. Now, there's a point I mentioned on this slide that I want to expound. This point we call process switch. Process switch can waste a lot of time. So let's see how that is done when you have program, okay? So switching from one process to another, okay? For example, if I have a task that is being performed by this particular process A, and it has to be done by another process B, we have something called context switching. Context switching simply means I am moving from one task to another. And context switching involves several things. It has to be involved, for example, it will have to involve things like this one here, memory management unit. Because when you context switch, you are basically moving from, for example, you are moving from this address space, you switch here from user space to the kernel space, then you are at the kernel space, switch again to the user space, and then you implement. This is what you call context switching. And it involves memory management unit, translation look-aside buffer. So basically, which is a cache that manages virtual address translation. So context switching can be very expensive, okay? It can be very expensive. So we don't want to utilize things that will waste a lot of time. So when we are using processes, therefore, we are involved in this context switching process from one process to another process, okay? And each process has been given its own address space. So that means that we have a problem in terms of we are wasting resources. So the interaction of this, of course, is in the process communication that we have discussed before. So when we have cooperating processes, there will be the problem of context switching, which is expensive. Expensive in terms of utilizing the resources that are on that particular computer. Okay, so you can see here, we moved from here, so we have the switch from S1, we come down here to this location here, from the user space to the kernel, and from the kernel back to the user space for S3 here. Okay, so from S1, S2, and S3, which is context switching, which is wasting space and time. Okay, so we want to utilize things that do not, require a lot of this context switching, and that's where threads can come in. So let me expound on context switching. We'll come back to threads later on. So the context switching happens, when, for example, we have a process exists. So when a process finishes a task and exists, we have context switching. Okay, remember, even the memory location has to be reacquired to be allocated to others. When a process uses its time, we have context switching. When a process requires another resource, for example, some of the things that we have discussed in computer organization before is that when you are using a file, that is stored on a hard disk, the cache will be involved in buffering that information to be brought to the client side. Now, the computer is not going to wait until that is complete. It will pick another task to be implemented. So that process that was being used might have to relinquish that memory space so that a new one can utilize it. So that's why I'm saying here, we might have a scenario where a resource requires something that is not available and needs to wait until the input output is complete. Okay, or maybe a resource has become available and maybe it was a sleeping process has gotten the information that it requires and it wants to start. Again, the kernel will set it up. Context switching takes place. Or a process relinquishes the CPU that it was using, okay, using a semaphore. So basically, these are for identifying maybe the long distance calls for particular implementations that were taking place, or even another system call. So there's a lot of context switching that happens when the computer is handling the tasks that it does on a continuous basis. And therefore, utilizing processes is quite expensive. Okay, so let's try to see how we can limit that. Here comes now what we refer to as lightweight process. So remember, I had a process and I've said I've given disadvantages. So let's try to find a better solution. In comes a lightweight process. So a lightweight process, okay, is now just to recap, the process can only do one task. Okay, so a lightweight process gives us an opportunity to do multitasking. So it means, therefore, that with a lightweight process, instead of me performing only one task at a time, which is sequential, I can do multiple tasks. Okay, I can have multiple tasks. So I have multiplied my capability by saying, instead of performing one task, I can do more than one task, which is a good thing. So that's a characteristic of a lightweight process. But in contrast to a full-blown process, lightweight process can share its address space. So you notice here, now, a full-blown process could not be able to share its address space, but a lightweight process can share its address space. Yeah, so you notice here, it can share address space and the resources. So you see, we have brought in two advantages. It can multitask and it can share local address space. So you can see how we have multiplied the capability. It can share and it can have multiple tasks. Therefore, okay, a lightweight process is much better than using a process. Now, so let's now go further and now think about a thread. Okay, a lightweight process has its own process identifier. Remember, it's just like a full-blown process, but it has parent relationships. Remember, these parent relationships are obtained from this concept where we said, okay, they are obtained from this concept where we say it can share an address space. That's what we mean by parenthood relationships. Each has its own private identifier, yes, but it can, within the relationships, the parent relationships, it can be identified, but it can share. Okay? Then it behaves exactly like a full-blown process. So that means it started at the kernel level. So it started at the kernel level, managed at the kernel level, just like a regular process. So a lightweight process has the same characteristics as a full-blown process. The only difference is that it can share address space and it can also, it has on its unique identifier and it can multitask. There are examples of this. The Linux kernel behaves like that. The way it behaves is like a lightweight process. I'm going to talk about a thread on top of that, but in a short while, okay? So we have two things. So we have a process and we have a lightweight process. and we have looked at the advantages. We have looked at the disadvantages of a process so that it can give us a chance to say a lightweight process is a better implementation of a distributed environment. But is that sufficient? Okay, is that sufficient? No. So let's look at the advantages before we look at how to even improve this. So, okay, lightweight process is used for cheaper thread management. I didn't mention that earlier on, but we can use a lightweight process for thread management. I'll expound that. A blocking system call will not suspend a whole process. Remember, blocking, in our discussion, when we are using remote procedure call, we said blocking means that that particular process will have to wait until the result is brought back. Lightweight process does not have that problem. A blocking system call will not suspend an entire process, the whole lightweight process. So it means that if I had multiple tasks being done, only one task will be, the one that is blocked is the one that will wait. The rest will continue. So you can see functionality still continues, okay? And lightweight process is transparent to the application. Remember, we are hiding, so we don't have to know what is happening, and it can perform several tasks. And lightweight process can easily be mapped to different CPUs. So if I have multi-core kind of environment, I can have a mapping of lightweight processes at different CPUs are being handled at different times. So, and that means that my capability to handle several tasks has improved. So, but is that sufficient? So we have looked at a thread. We have said it has, not a thread, process. We have seen its problems. We have looked at a lightweight process, which is an improvement, but it still has its own problems. So how do we now move further? Okay, so we introduce threads, which is we call thread implementation. Okay, so now when we talk about threads, we have here, let's start at this moment here, this point here. So we have discussed that processes and lightweight processes can be set up and handled by the kernel. It's the one that will give the resources that are required. Okay, but a process cannot share its address space. A lightweight process can be able to share. So the first thing at the kernel level, we are saying that a process can share address space. So we minimize resources. Now the next thing that comes now, we have threads. Now, a lightweight process can have several threads running on top of it. And that's why you can see threads are now at the user level, and threads are implemented at the user level. So we have them at this user level. And they're running on a thread which shares an address space. So you can see we have now really shared the resources. And that means that I can be able to multiply my functionality a lot because I can be able to share the resources. And at the top here, I can have multiple threads running on a single lightweight process, okay? So therefore, manipulation of threads at the user level is now much easier, much cheaper. A blocking system call, like we have said before, doesn't suspend an entire process, so those threads will still continue running. And applications don't need to know which are the lightweight processes that were handling that, and we can have different lightweight processes on different CPUs. We have managed to be able to multiply the capability of the environment by using this concept. Okay, so therefore now a thread, okay, a thread is a specialized process running on top of a lightweight process, which is utilizing minimum resources. And hence, we have capability of doing several things. Okay, so therefore, a thread at the top here basically makes it easier. So now, in my distributed environment, I can have so many threads running at the same time, much cheaper, and handling so many tasks. So, and therefore, lightweight process here allows for multitasking. And of course, we share that address space and other resources. And hence now, I have a lot of capability. So a distributed environment, we use threads. They run on top of lightweight processes that share an address space. Maybe at that moment, I think I can maybe handle a few maybe questions before we proceed. Okay, okay, so I think when I explained that was, yeah, so that is covered. Okay, so anyone else maybe with a question? Someone had a question, but when I was explaining, I answered that. Okay, so let's maybe expound that concept now to show now what really happens figuratively now. So now I have here, so we have the kernel, okay? And now the kernel threads here, remember, we want them to be lightweight processes, okay? And then now at the top, you can see what is happening here. We now have this one here. And you can see I have several threads running on top. So I can see these ones here are running on one thread and one lightweight process. This one has two. And remember, each of these ones here, each one of this one here has a capability to perform a function. We'll see those examples later on. So it has a capability. So you can see I have multiplied that, which is a very, and that's what I call a hybrid implementation of this. Very, very key in terms of a distributed environment. So let's see some of the ways it can do this. So assume maybe, for example, we want it as a server to implement tasks. And so we're using what now can refer multi-threaded servers. Okay, and remember, each thread has capability to perform a function. Okay, so now we have a request coming in. Oh, sorry. We have requests that are coming in here. So we can queue those requests. And then now we have, let me call that, maybe for example, let me call that one a dispatcher. So basically it will handle the different requests that are coming in. And then these ones here, these ones we can call them worker threads. So you get task A, you give to one, give B to another, C to another. And so, and remember, this can be running on top of one maybe lightweight process. Because remember, if they're coming in from here, they are managed and controlled, maybe sequential in a queue format, and then this one here will handle them. At this moment, the dispatcher will handle them one by one, and then gives to the worker threads, which will handle each of those requests. So you can see several tasks, and this implementation is at the user level. So this means that if I was, this diagram here was a server, you can see I have capability of handling different tasks. And so this is the benefit of threads, multi-threading, and hence multi-threaded servers among other applications. Unix has a similar way of handling this. And I'll just show you maybe how the program will look like. So we start, we can fork a new maybe thread. If it's 0, you exit, else you have that, and then you can be able to implement. So it basically forks new child processes. So when you make a request, the Unix program will here is calling it a separate process. I was just using this as a way to show if you are using a Linux maybe server that is using multi-threading, okay? So this is the kind of scenario that can happen. So it is forking new threads, okay? And by the way, I should be able, let me warn you that when you are reading different textbooks, there's a possibility that you might get to a point where there are interchanging the term process and thread. And that's why I was very key to focus on trying to explain the difference. So as we go ahead, as we discuss, when I'm looking at the implementation of the distributed environment, look at it from this point of view, okay? That the actual implementation of the working is done using the threads, okay? But the term process is generic, is used in a generic form. So don't get confused when you see and look at it that, oh, we mentioned that, oh, threads are used in terms of implementation of tasks, and yet, different textbooks are using it different. So please don't get confused there. Just remember that it's in terms of implementation, people can use the terms interchangeably. Now, when we are using, in a distributed environment, we need to have processes, of course, cooperating. So they have to work with one another, okay? So if it's a sequential programs, so it will be a single process, which is a big issue, okay? If they're concurrent programs, that means that we need to do things concurrently, okay? We execute concurrently. And the advantage of this, basically, concurrency speeds up application. And that's why multi-threading becomes good. So we need to do things in concurrency, okay? And so things like web servers, Windows systems, basically benefit from this concept of concurrency. Just like the Linux server environment that we have talked about. So the motivation, therefore, for someone to decide to use threads, remember, we can simply say thread process creation is expensive. Like that fork call, so it's expensive, okay? Context switching. If I am dealing with one process to another, context switching is expensive. I gave examples there. Inter-process communication requires kernel intervention. Okay, so anything that requires kernel intervention is expensive. So rather things don't have that, okay? Because if we are having one lightweight process, the intervention is only through that one, okay? But if there are several of them, that becomes expensive. Cooperating processes, okay? No need for memory protection, okay? Need for memory protection because of the separate address space. So, sorry, this is not correct. I need to use need for memory protection because they're using different address spaces. Please remember that part. That was a mistake there. So that's why we are motivated to use threads in our environment of a distributed environment. So again, just one of those things that we mentioned. So I have a kernel there, and I have threads, and the thread you can see. So you can see here, even the term, they are calling it process 1, process 2, like I said, okay? So the utilization, I mean, the terminology sometimes can be in that, can be a problem. So this one here, one thread, and here we have thread that has several. So that has several of them. So we can have this one here, process with one thread, and this one with several threads that are involved. Now, maybe someone might wonder, okay, so how does this work at the user level? How do they cooperate? Okay, these processes, how do they cooperate? So this is a good example of how this can cooperate. We have our kernel there, okay? And we have one thread there, another one, and another one, okay? So we have three threads, 3 stacks. So each one, of course, will have its own stack. Let me just check something. Sorry, there's something I missed here that I need, sorry about that. So the difference between those threads, key is this one here. This is a process, it requires its own address space, its own global variables, its own open files, child processes, pending alarms, signals and signal handlers, and then of course accounting information. Each process must have, okay? So this one here is saying each process must have this. Sorry, I need to be using something else. It has this. Now, if you're looking at a thread will have only per program counter. It will have its own registers, of course, stack and states, because remember, when you're running a program, it has to be individual. So in this case, it has its own register stack so that you do not confuse information. So now, in this case, you can see process require a lot of information, but okay, if you look at the thread, the information required, I mean, the independent things that each one requires is less. So all items shared by all processes are here, okay? And these are on the right-hand side. Those are things that are for each particular thread, okay? So if you are having a full-blown process, you can see it's very expensive. In addition to what is on the left, it must have what is on the right. But if you are using threads, you will have, they share what is on the left, and each one has independently what is on the right, okay? And that is what is now shown on this particular diagram here, okay? What I was showing earlier here, yeah? So you can see it has its own, each one has its own stacks, okay? Counters and so forth down there, but it now has independent information for each one of thread 1, 2, 3, 4. Well, 1, 2, and 3 years here. Okay, so there is the shared, which should be below here. Okay, and then the independent ones in the user space. So why? And these threads, of course, can cooperate. Let me show an example of how this can cooperate. And I think when we do this, when we finish this one here, we can field questions in regard to this. Supposing you are typing on your keyboard, okay? On your keyboard, you have your keyboard here. So you need a thread to keep tab of what you're typing, okay? Then you are communicating with a disk. You need to keep tab of that information that is being sent from there. And then of course you have your screen where you are typing. Now you notice here, so we have one, okay, yeah, to take care of your screen, another one to take care of your keyboard, another one to take care of your disk. And you can imagine if you're using a complicated program, okay? So it might have to have several threads handling this. And this is where this task, when it came in, when this task came in, it was one request, but you can see we have several things that are required, and hence the importance of trying to ensure that we have different tasks. Okay. Okay, so the importance of ensuring that we have a different thread that handles each of those tasks. And just to recap that, they will have something like this one here, which we mentioned earlier on, which basically means that we have worker threads. So one will handle, maybe for example, if I'm accessing maybe the web page, one will handle the web page cache, another one will handle maybe my process, my application part, and another one will handle maybe the network connection and so forth. So all this, of course, are handled by the user space. So you can see in what, and that's why it's called a multi-threaded server, web server. So we have one server handling a different task at every different time. And this multi-threading is that's what makes distributed applications and environments to be functional. They can be able to function pretty well. Okay, I think it's time for questions. Okay, so when you have, okay. So let me start with the first one, where you're asking, why is it less expensive when a thread is running at the user level than at the kernel? Okay, let me start by saying that threads, of course, only run at the user level. Okay, the diagram I had earlier on that was showing a lightweight processor has that. So it runs only at the user level. Now, the point of why is it less expensive? Okay, we have said when we started, a process requires its own address space, and it has only one thread of control. Now, if I have a thread can share an address space with other threads. So you can see, if I had a cost for one address space, I have an address space that can be shared. That's less expensive. Secondly, we also said threads run on top of a lightweight process. And lightweight processes can share an address space. So remember, I have already shared the address space for several lightweight processes, and each lightweight process can have several threads and hence less expensive. Do child processes also use threads? Of course, child processes, okay, we can refer to them also in terms of threads. So that concept of forking that the Linux uses is basically the same concept of child processes. And that's why I said earlier on, I warned you, sometimes you can easily confuse the term thread and process. So they're actually, in terms of implementation, they're actually threads. It's just that we are supposed to call them threads, but we are just saying child processes. And so, and they are child because they are sharing the parent's address space. Okay, so that's why they are child. Okay, and so they are basically threads. Okay, another, maybe someone who has another question, maybe something. Okay, so I have another one coming up. Okay, that's done. Okay. Okay, so I don't want to pick on something new. So how is it going so far? This course can be very technical, but I'm trying to take my time to explain. I don't know what is your view so far in terms of some of those terminologies and the time I'm trying to explain. Any comment? We have the chat, so feel free to comment there. Hey, are you still there, or you have or you have left? Okay. Okay. Yeah. So I have comments here. Okay, I get your comment. That's okay. So fine. So I'll take the comments. Thank you, Joseph. Madenka, I got your comment. Joseph, I got your comment. So I will, as we go ahead, some of them will have to see how to implement. But like I had mentioned, this course at first, when you start, some of the things can be very theoretical. And that's why I'm trying to pick a few examples, but some of those comments will pick them. Okay, so so now I think I want to stop there today so that we can pick up on next week. I hope some of you you managed to upload on e-learning. And if it was not possible, I think I have sent some way to handle it, but I can go and check tomorrow again. And the other topic, now we finished communication. So I have sent a few questions. I think that is tutorial number 2, which should end again next week. So please try to look at it. And then again, you can, I'll set up where to upload the moment we are ready. So I think, thank you very much. Maybe you can go and complete some of those tasks if you have not completed. Have a good evening, and see you next week.